This is video 2 in the introduction to our video module. And in video 1, we did an introduction on and talked about what R is, talked about the R related resources for our class, talked about the features of R, the outline of the material that we're going to cover from the book. And then we ended up talking about RStudio and went through an example of how to use it, the IDE, and what some of the other components of like R Markdown and R Notebooks and Shiny and other things that RStudio promotes. In the second video, we will focus on the basic R programming R script, and we will talk about basic R programming, as the name would imply. So R variables are like Python in that they point to an object, and so the variable themselves don't have a type. The object itself has an inherent type, and so you can change that you can change to where the object to which the variable points, and thereby change the type or the imputed type of the variable. So we're going to show that here in just a second, and then we're going to talk about object types and data types. So we're going to vectors, lists, matrices, arrays, factors, and finally data frames. And it's data frames that are going to form the primary focus of the material that we cover in the class. But we need to cover some of these other types to support the notion or to support the understanding of what a data frame is. Data types, we have logical, numeric, integer, complex, character, and raw. We'll focus primarily on the logical, numerical, and character. So we're not going to deal with complex or raw, but I will give a slight, or I will show an example that we got from the tutorials point tutorial. So for this video, we'll focus on using RStudio. And so you can see that I have just opened RStudio. My global environment is empty. I do have the course project open, the tools for data analytics and modeling project that we talked about in video 1. And so I want to demonstrate just a couple of items here. So first of all, I'm going to open the Hello World, the very simplest script that we can have. And I want to focus on how to execute code in RStudio. And there are a couple of different ways that you can do this. First of all, if I highlight a line, I can just click on Run, and it will execute that line of code. So if you mouse hover, it'll say select current line or selection, so I can select multiple lines. So there you can see I didn't have anything selected, so it just executed the first line. If I execute the second line, then it will actually print. I can also highlight both lines, click on run, and it will execute those both at once. So this run lets you run the current line. I can also rerun the previous code section. So without selecting, I can just do Control-Shift-P. The second general way is I can use the source, and what source does is it sources the whole document, so I don't have to select anything. So if I click source, you can see that it runs both lines as it did when we had both of those selected. I can also run source, and I can do source with echo. And so source with echo will then echo the statements back so that you can see the execution of the individual lines also. And then finally, I can do source as a local job. And so if I do that, then I can execute multiple things simultaneously. And so, for example, if I just click on Start, and then I can go over to the tab here. So I was on the Console tab, and if I go over to the Job tab, you can see that it obviously already ran because this is a very simple script, so it doesn't take any time to run. But if using the source as jobs, then I can be executing multiple things at the same time. That's fairly complex things that you would use when you have long-running scripts, and we're not going to see much of that in this class. So we're going to focus on the simple invocation. And so what I want to do is I'm going to open the basic R programming module here, and we're just going to go through and execute some of these things line by line and discuss what is actually going on in these. But before I do that, one thing that I forgot, I wanted to show two more things before we get to the actual code. Sorry about that. I want to show two sample R notebooks, since we talked about that before in video 1. So I have sample R notebook, and RMD is the R notebook. And you can see that it looks similar to what we saw in Jupyter Notebook, where we have the notebook notion, where we have different cells. And in the R terminology, then you have what are called R chunks. So I can see some R markdown here. And I gave the reference here to, if you want to look up the R Markdown code and how to use R Markdown, we have that reference here. And then when we have the 3 tick marks R, this is saying this to treat this as an R is R code. So we'll show this plot cars when we get to the visualization, but basically what that does is it creates a plot of an internal data set, which we will see. And so you can see that I just executed that, and then it did this kind of in line. Well, it did it actually in line. And so we can have that chunk of code that was executed. Then I can have a separate R chunk and use the question mark, which is the R syntax for help. So if I do help on cars, it will then open the help viewer and say, okay, well, this is what the cars data set is. And then you can say, well, what are data sets? So you can look at that and it will tell you what the data set package is and so on. So the idea of a notebook is that you can have these code chunks interspersed with Markdown. You can use the Markdown as an annotation mechanism, and then you can execute the code. Then you have several features for distributing this. So the one, if you look at the knit option, you can knit this into several different formats. So for example, if I just do knit to PDF, it's going to generate a PDF document. So let me just drag that over here. Oops, that was created on the other monitor. So there it is right there. If I could grab it. Shrink that down so you can see it. And so this created a PDF document. And you can see, so this is something that you could say, for example, turn in or share with people in print form. Or you can share the notebook and they can then execute the code. So it makes it really simple to distribute and to work interactively. The second one I'm going to demonstrate before we get to some of the R code proper, let me close sample notebook, is the notebook with other languages. And so you can see that this is a very similar structure. It is a notebook structure, the RMD, so you have the chunks, and then I have an R chunk here that's got R right here. Then I have a different R chunk here where I'm going to use the tidyverse, which is something that we will see a little bit later on. But I just wanted to demonstrate this because this has somewhat sophisticated behavior in that you can iterate between the console. You can switch back and forth between the console and the graphical view. So here's the graphical view. This is a histogram of a particular data set. And then I can jump back to the R console and see the output. And so I was showing some of the statistical data about this particular data set. So you have that kind of interactive behavior. And you can also have a Python chunk. So in this case, I say, I have the 3 tick marks here, and I'm saying, hey, I want to execute these as Python. So I'm telling it what the path is for my Python, and I'm using the Anaconda Python. And so when I execute this, you can see that it just executed my Python code. Success, success, we all love Python. And so note that when you do this, then when you execute this, you might have to install different R packages depending on how your system is configured. So if you've never done some of these things, like when you do knit, you're going to have to install some support packages. When you want to execute external Python, then there's some support packages and so on. So you will see a notification say, do you want to install packages? And then finally, I have this demonstration here that we can connect to MySQL. So I have the MySQL database that we have set up for the class, and it's already there, and I can access that, create a database connection, and then if I want to query the database, you can easily do that also. So the notebook metaphor here, or the notebook structure here, gives me this nice convenient way of displaying all of this information. And then, as I said, if I go here and say, well, let me open this one again so that we have all of these, I can then preview and I can knit this. So if I knit the PDF, it's going to generate the PDF file, execute the external code. It's doing that here in the background here. So let me just wait for a second while it generates. Looks like we have an output file somewhere. Oh, it's still executing. There we go. Executed, and so now we have my output, and you can see that it did a ggplot, and there's the plot that we had. There's my Python code success, and then here is the here's the MySQL code. So again, something that you can either give or turn in or share in PDF mode or in Word mode or in HTML mode, or share the notebook file, the RMD file, and then who you're sharing it with can actually execute the code. So that's a really convenient structure we will see a homework assignment where you guys have to build one of these R notebooks as the for what you submit for the homework. Okay, so back to our basic R programming. So the first thing I'm going to do in the global environment is I'm going to click on this little broom icon, which basically removes all the objects from the environment, just so I can get us back to where we were before where I demonstrated the R notebooks. And so here we are back to the code that we've seen before. So what I want to do is I want to execute these, and I'll just execute these one line at a time. And as I say here, in the note the my string in the global environment with my nice little arrow saying, hey, look this way. So you're looking over here and you can see, okay, my string is the variable and hello world is the object that variable points to. And so that creation, this was an assignment statement where I assigned this object, where I created this object of type character, and then assigned that to the variable my string. And then I can use the print statement to print the variable or print the value here. So you see that print there. And then also when I execute the second line where I say, okay, well, let's assign a different value, you can see that it just overwrote that value here. So exactly what we saw before when we did Python is that we just created a new object and then and then set that variable and then got rid of the anonymous object since nothing else was pointing to that. And so I showed this before earlier where you can clear from the workspace using the broom, but I can also use the rm command. So I just go down here and type rm and rmistr and then enter. You can see again. So you can either use the broom to clear the environment. You can use the rm command to selectively delete individual objects from the global environment. Second thing, and we've actually seen this in module one, in video one, when I know what the current working directory is, so I can either print that, which is what I did here. So I just print the return value from that function. It says, okay, here you are, and this is where I store my GitHub repositories, and so here's the root directory. And so I need to know that when I either read or write files, or I need to access files that are somewhere else within my directory structure. I need to know where the current working directory is. And if for whatever reason I wanted to store that, so I can create a variable CWD. So if I want to say open a file and I just want to prepend the file name with the current working directory, then it will locate the file for me. And I don't have to use the absolute file path every time, assuming that is on the current working directory path. So again, something we'll see as we move forward. Okay, so let's talk about some of the R data types. And so the first one is the logical type. So in this case, again, I made an assignment. And note also that we have this assignment notation where instead of the equal sign, we use the, what would that be, less than and then a dash. And so that's just a traditional way that R uses to say, store the value true, which is logical value, to the variable condition. We can also do condition equals true. So I can do that also and I end up with the same thing. But this is the typical way that you will see R code referenced. And if you're more curious about why that is, well, I don't actually know. So you can go search, which I did. Basically just went and said R, the typical assignment versus the equal, what are the differences? And then of course we see a Stack Overflow response, which gives us more detail. The checked answer, the most popular answer, basically goes through some of the details of what that difference is. So I will let you have a look at that if you're curious. But what I typically do, or almost always do, is just use the standard R assignment. So we can assign the value, and then I can override the value and assign it to false. And we can look over here at in the global environment, and we can see that now the variable COND condition is equal to false. I can use the class function to say, hey, what type is this? So class condition says, okay, this is a type logical. So logical variables are like Boolean variables in Python and some other languages. It's either true or false. Numeric is another type. So you just, in this case, I assigned the value of 197.8 to the variable x. And so we can go over here and see x is 197.8. If I display X, I can see that. Just in R, you can just display the value of the of an object by just typing that. So if I go X here, then oops, I didn't mean to do it there. I meant to do it right here. So X, you can see that. Or I can look at the class and note that the class here is numeric. And so this is a floating point number, but you can see that it's in R, it defaults to a numeric class. So if we assign an integer, so 27 to a value y, so there's y and there's 27, show the value and look at its class, and you can see that its class is also numeric. So unlike in Python, where you would explicitly differentiate between those types, in standard R, or unless you have a reason to do that, you would just default to the numeric type. Now, if you want to specify as an integer, you can do that either by using the L notation here. So if I just say z is equal to 7L, and I look here at my global environment, I have z and I have 7L saying, okay, this L says, okay, this is an integer, a long integer actually. And look at class and it says, okay, this is a class integer. Or I can use z as integer y, and then I end up with the same thing. But then if I look at the comparison to z equal y, so I created z using the as integer function to y, so now z is 27L and y is 27. If I say are these two equal, then they are. So R knows how to do that comparison. And so hence my note, unless you want integers for a specific reason, then you should use the default numeric. And so if you don't know what a reason might be, then you should just default or use the default of numeric. And if a situation arises where you need integer, either for a particular function or a particular application, then have a look at the details of that situation. So I also mentioned you could use do complex numbers, so 2 plus 5i, and then if I look at V here, so I can see V in my global environment, you can see it there, or I can see it here. I can check the class, and so it's a complex class. Character values, so class variable A has a value of A, and I can see that here, or I could look at the class as character. Strings are also class character. So if I assign a string, this is a string to the variable s, there's s, display the value, and then the class, again, is character. So it doesn't differentiate between a single character and a string. They're all objects of class character. For whatever reason I want to store raw data, I can do that. So I just do char to raw, and I just happen to do blink in this case, and you can see V now is a list, and it's storing those as hexadecimal. So 42 is hexadecimal for cap B, 6C is hexadecimal for little l, and so on. So you can then look at those values and look at the class as raw. So these basic classes that we see are numeric. If you want to do integer, you can do integer, but as I said, there's no reason to do that unless you have a compelling reason. Complex, character, and then if we need raw, then you can define the raw data. Okay, so now that we have the object types, I'm sorry, the data types defined, so we talked about logical, numeric, integer, complex, character, and raw, we can talk about object types. And so you can see here that vector is listed first, and a vector is the basic object type in R. And so when I execute this statement, let's clear this, I guess. Let's clear that, clear the environment, and then execute the statement. When I do z is equal to 27.5, which we saw before, a simple assignment, what I'm actually creating is a vector of length 1. Right, so you can look down here at using the length command, the length function is length 1, and so we've created what's called an atomic vector. And so this is one place where having a look at the tutorials point can be beneficial, can be helpful in talking about the details of the vector creation, and so all the different vector types and so on. So this is a good place to have a quick look at the tutorials point. I'm not going to do that in the video, but that's something you should do. I've got some of the other components of that I've extracted into my little example here, but it'll be beneficial for you to look at the whole component or the whole part of tutorials point. So if I want to create a vector in the traditional sense, or a vector non-atomic of length greater than 1, we use this general format of C for create. I guess it's for create. I don't actually know. I've always thought of it as create. And parenthesis, and so when I execute here, you can see that I've created a vector with indices 1 to 8 with the corresponding values. So I can print that and print the vector. I can look at the length, and it says, okay, it's the length 8. I can do the class, and so, class run is numeric. So I can look at the class of X, and so it knows that it is a numeric vector. And so our vectors are of a single type, and so you can't mix types within a vector. And also, our indexes are 1 base rather than Python's 0 base. So if I look at X 1, then I get the first element, which is 12.2. Whereas in Python, which is 0 base, X1 would give me the second element, 17.8. So sorry about that point of confusion between the two languages. I can also, if I have an atomic vector, which Z is 1, you can also use that index notation, and I can access the first element by using Z1. I can define sequences by using the colon notation. So I'm assigning a sequence from 5 to 13 to the variable v. And you can see what that did was create a vector starting at 5, including 5, going up to and including 13. So again, unlike Python, where you used the default slicing and range, it includes the starting um, component up to but not including the final one, but in R it includes the final one. So that's an artifact of being 1 based and not 0 based. So when I use sequence 5 to 13, I get the value 5, I get the 13 and everything in between. I can specify the step or the stride. So in this case, I can use the sequence function and define a sequence from 5 to 9 by 0.4. And you can see that here. I just printed it. I didn't make an assignment. So I just printed the value. And you can see we start at 5, we end at 9, and the stride value is 0.4. If for whatever reason I wanted to save that, then I could incorporate that. So let's just go over here, copy that, and let's just call it temp, and then make that assignment. And so when I make the assignment, then I have my temp variable, and you can see that the starting value of 5, the ending value of 9, and the stride value of 0.4. Okay, so again, when I look at, when I typically would think of integers, so when I go from create a vector of size 3 with 3 what look like integer elements, you can see that when we do the class, they are numeric because we did not specify. If you want to specify, you can, as I said, either using as integer, which we see right here, or using the L notation. So I can either use the as integer function or the L notation. And then when I do that, then you can see that it's created of the vector with class integer. But once again, the note, unless you want to create integers for a specific reason, just use the default as numeric. I can have character vectors. So red, green, yellow is our apple type. Jump over here and look at apple. You can see that we have character type, 3 elements, red, green, yellow. I can print that. I can print the class and see that it's some character. For selecting elements and slicing, we've already noted that we can access an individual element using the index, in this case the 4th element of X. And remember again that it is 1 base, so 1, 2, 3, 4, our value of 35 from 4. I can also use a sequence. So when I do a sequence between 3 and 5, we're going to get the 3rd element, the 4th element, the 5th element. So 54.4, 35, 68. We can also specify particular values. So in this case, note this internal, the slice component is itself a vector. So I'm creating a vector 236. So when I execute that, oops, I didn't mean to highlight that part. Let me just run that line. it's going to first, well, I guess that's a good thing. It first created a vector 2, 3, 6, and it says, give me values 2, 3, and 6 from the vector. So the second one is 17.8. The third one is 55. 4, 5, 6, then, of course, is 55. So one difference between Python is that when we use a negative index, that doesn't mean it starts from the end. It's a little bit different. What this is saying is remove that specific element. So if I do x minus 2 and run, you can see that it returned a vector with element 2 missing. So if I look back over here to x, my element 2 is 17.8. And if I look at the value that was returned from my minus 2, there is no 17.8. So what it did is it took the vector x, removed element 2, and then returned a new vector to me. And I can also use in this case, an internal vector to specify specific values to remove. So in this case, 2 and 5. And so again, you can see that element 217.8 is gone, 3, 4, 5, 68 now here is also gone. Okay, so you can use that negative to remove specific values or remove a sequence of values, remove a set of values. It's very powerful in terms of what it, how it allows you to remove specific elements. Also note that the variable x doesn't change. So in this case, I have returned the value, or I'm sorry, returned a vector with those values removed, but x hasn't changed. But what if I do this assignment? So in this case, if I do x minus 2, and then assign that to x, and then as I note here, ooh, this should be a t, watch the, not watch he, yeah. So watch the environment with repeated execution. So if I just click and watch this, you can see that the 17.8 disappeared. And then if I execute the same bit of code again, now the second element is going to be the 55.4, so it's gone. And now the second element is going to be the 35, so it's gone, and then and so on. So I could repeatedly execute that. And what it's doing is it's creating a new vector, and then it's assigning the variable x to be the newly created vector by removing that value. So let me go back to the original. I don't know what OR is, but let's do back to, I guess I mistyped that. Go back to the original, so now we have our original x vector um, in our global environment. So whereas vectors have common types, so all of the elements of a vector have to be the same type, lists can have different types. So for example, if I create a list using the list function, and I create a list that includes, in this case, a vector, C123, a numeric, 21.3, and a function. And then is the note here, check the environment. So here's my list. So this is a list of 3. And I can then click on that, and it will open it up over here in the left pane where we typically look at the files, and you can see that element 1 is a list of 3 doubles. Element 2 is a list of doubles, so these are again numeric, and then element 3 of my list is a function. So we have a list, we have a vector. We have a vector of length 3. We have a vector of length 1, or an atomic vector, and then we have a function. And so I can print the list. I can look at the class, and this is a list. I can look at the print the second element, which is my number 21.3. If I look at the class of the third element, then it's this primitive function, sign function. I can also do a list, in this case where I have a sequence, and then I can look at the individual values. List 2 is my second element in the value, so it's this one right here. I can look at the vector C2 and 3, and so of list 1. So we're back to list 1 where we have the second and third element, and so that is my 21.3 numerical value, and then I have my primitive function. And then secondly, I have this notion of why are these two different? So in this case, I'm creating a list, so click both of that. So before we actually look at that difference, note that I have both of these on the same line. And so you can see that we created a list X and X2. So my list X1 has 4 elements. right? So that was the one that's created here, and so that's just what we would expect, 1, 2, 3, 4. And if I look at x2, then it's a single list, and it's a single list of integers, 1, 2, 3, and 4. So it created my sequence 1, 2, 3, 4. And then if I look at those lengths, you can see that the length of 4 or the length of 1. And finally, I create a list x3, and this list creates 2 sequences, 1 through 4 and 5 through 8. So it's a list of 2 elements, and each one of those elements consists of an individual um, list. And also, as I note here, have a look at tutorials point for examples of using element names with lists and other examples of um, how to use the list notation. A matrix is a two-dimensional matrix or two-dimensional vector of values. And so you can see I created a sequence 3 to 14, and then I specified the number of rows 4, and then I used the by row parameter, set it equal to true, so that it created a sequential by row. So you can look at the environment here, and there's my M value, and let's just click on that, and you can see that it's my values are sequential by row. So 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Whereas if I say by row is equal to false, which I do in N, if I look at N, now I look at N, and I still have a 4-row, 3-column matrix, but now the numbers are sequential by column. So 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So by using the by row parameter, I can specify whether I have a row major or a column major matrix in my definition. I can also define row names and column names. So I just define 2 different vectors. One is called row names, one is column names, and then I can specify my dimension names. So my dimension names here for rows and column is specified by a list. And then there you go. You can see that now I have row names and column names. So very similar to what we saw when we did data frames in Python. I can access elements um, of my matrix. So 1, 3, 4, 2. I can access a particular row, so I can use this slice notation, 2 comma, and there's my 2 comma, so this is the second row. I can do the third column, so a blank comma here. And so note I'm going through this really quickly because our focus here is going to be on data frames, which we'll see in the next video. But it's all workable or all doable with matrices. And as I said, you can check in tutorials point for seeing more details of this and also seeing how I can access individual elements using the row column names. Arrays are similar to matrices, except you can have more than 2 dimensions. So I can have 3-dimensional, 4-dimensional, 5-dimensional, and it supports all of the same things that we just saw, the same structure that we saw with matrices. You can have dimension names and so on. And so if that's something that you would find useful, check tutorials point or another tutorial source or reference source to see the details of that. So that's the end of the video number 2. In video number 3, we'll come back and talk about factors and data frames, which are going to form the major component of what we focus on in our class.